Hey everyone and welcome back to PrepFusion. So up until now you have studied the basics of vector algebra. So we'll continue with basics of vector algebra. We'll do few questions on vector algebra and vector calculus, and this will be a fundamental building block for our EMT chapter. Okay, EMT total subject. This will be a fundamental block. So first there will be two lectures, lecture 0A and lecture 0B, where we'll mainly cover the basics of vector calculus, and then we'll start with the main electrostatic and magnetostatics portion. So yeah, let's start basically today's lecture will be 0A. So let's start with the question itself. So I know you have covered basics, so we'll do a few questions on those basic things. So let's do this first question. So in this question we have a vector field V, which is given in terms of the unit vectors ax, ay and az direction. The unit vector in the direction of v vector at the point 1, -1, 1. So this is pretty simple, right? So like this is the concept of directional derivative if you have done calculus, vector calculus, but it's not exactly that. So first of all we have to find the unit vector in the direction of v, and then we have to put the points, right? That will give us the vector. Okay, so first of all whatever we'll identify, that will be a, whatever we will find out, that will be a unit vector. So I will write what is a unit vector in the, like for v, what is the unit vector of v? It will be simply y square, like vector v, magnitude of vector not there, sorry, vector v divided by magnitude of vector v, right? Magnitude of vector v. Okay, so easier way, like you can do it in two ways. Either you first of all derive it in terms of x, y and z, then you put the values of x, y and z because they have given us x, y and z, or you first of all put the values of x, y and z and then directly find out the unit vector. So I will do the second option. So second option, I will put the value of x, y and z. So it will give it like here x, y is -1, so this will be -1 whole square into 1, so this will be 1 into ax plus 2 into 1 into -1, so this will be -2 actually, -2 into ay plus 3 x square az. So x is again 1, so it will be 3 az. Okay, so what will be the magnitude of this? Magnitude will be 1 square plus 2 square plus 3 square, so it will be something 9 plus 4, that is 13, plus 1, that is 14, so it will be under root 14. Okay, it will be under root 14. So this will be the answer basically. Like this is the solution. I will just write this in a more tighter manner, neat manner. So this will be under root 14. Okay, so yeah, this is the answer for this particular question. Let's solve next question. These questions are basic only, just to test the waters, just to keep you on the groove. If a bar or a vector is equals to ax plus 2ay plus -3az and b vector is this, the unit vector in the direction of a bar plus b bar. This is again a simple thing, right? Just we have to find the unit vector in the direction of this. So first I will resolve this. Okay, I will find out what is a bar, b bar, then I will divide by the magnitude, and that will give me the unit vector in the direction of a bar plus b bar. So v vector is equals to a bar plus v bar, which is equals to ax minus ax, so this will be 0, 2ay plus 3ay, that will be 5ay. Okay, then -3az plus az, that will be -2 az. Okay, so yeah, this will be this, and if I resolve this further, right, so if I find the unit vector of this, what will be the unit vector? I have to find out a v cap. So I will just divide by the magnitude. What is the magnitude? 5 square, under root 5 square plus 2 square, that is under root 29. So this will be 5ay minus 2az divided by under root 29. So these are just the basic simple class 10 question. Okay, but still I am doing it just to get us started with. So like pause the video and try this question out, and then again I will I will solve this question. So let's read the question. So given a triangle ABC with a vertex A, B and C. So I have a triangle ABC. I'll just draw the triangle real quickly. So a triangle ABC, this is exactly not a straight line. A, B and C. Okay, so I have this triangle and these are the vertices and the points are given, right? -4. So I will not, like, this will be not exact, but for A this point is -4, 2, 5. B this is 16, 20 and -5, and C this is -14, 10 and 20 respectively. Find the unit vector in the plane of the triangle that is perpendicular to the line segment AC. Now find the unit vector in the plane of the triangle. So this is a plane, right? So this is like this. If I just join two lines, do 2 points, they become a line. If I join 3 points which are different, okay, they totally make a surface or a plane. Okay, this is a surface, and I have to find out a vector that is lying in the same plane. Okay, this is not lying some other plane, in the same plane, and that is perpendicular to the line segment AC. So it should be perpendicular to the line segment AC like this, and like how many lines can be perpendicular to the line segment AC? One way can be this, another way can be this as well. Okay, this as well. Okay, now like I will just draw the locus of perpendicular lines to AC. So there can be this, 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 this. I am drawing a 3D figure. If you are able to understand that this is also perpendicular, this is also perpendicular, this is also perpendicular. This is a 3D figure. Okay, this is a 3D figure. I hope you are able to visualize this whole thing, right? Because it's just a line, and I am totally talking about 3D space. So this is a let's say this is AC, right? So this thing is perpendicular. This is also perpendicular. This is also perpendicular. So this whole thing, right, covers a total circle. But what do I want? I want only in this particular triangle ABC surface. So this is my surface. This is, let's say, this is the line. Okay, this is the line, and like this is perpendicular. Everything is perpendicular, right? Everything is perpendicular to this line AC because this angle is perpendicular, right? But I actually want in this surface itself. So there can be only one vector. Like this vector is also possible. It can be either parallel or anti-parallel. Okay, parallel or anti-parallel. So I hope you got the point. So how do I go about this problem? One thing I know, I can compute the normal vector, right? I can compute the normal vector through this plane. How do I compute the normal vector? Simply if I do this cross multiplication, AB cross BC. If I do the computation AB cross BC, I will get a normal vector to the plane triangle ABC. Okay, to the plane triangle ABC. Correct. So this will be my A n cap. Fine. Now if I have this AC vector, right? If I have this AC vector is somewhere around here, right? AC vector is somewhere around here. I can parallelly bring this here, and if I do the cross product of these two, I will get a vector that will be perpendicular to both AN and AC. So AC perpendicular to AC is something like this, something like this, something like this, and perpendicular to AN will be directly this only. I will get back this plane only, right? Because I have just computed AB cross BC, that is the perpendicular to this, and again if I take the cross product of this, I will get back here. Okay, so I hope you understood the visualization that I told you. Okay, so first I will find out a unit vector along the AC. Okay, if I find out a unit vector along AC, what will be that? So it will be simply position vector C minus position vector A. Okay, so what is C vector? C vector is -14 AX cap plus 10 AY cap plus 20 A Z cap. Now if I just subtract this with the position vector of A vector, ax cap plus 2 ay cap plus 5 az cap. What will I get back? Obviously I have to divide by the magnitude as well, that I will do. Okay, first of all I am just computing the ECE vector for now. What is it? It is simply minus 10 x plus 8 ay, then minus 15 is it. Okay, so this is what I will get, and if I just divide by the magnitude of this, I'll just quickly do the computation. Ten square plus 8 square plus 15 square under root is 19.73. So this whole magnitude is 19.73. So if I divide this into 10, this will be 0.5. X, obviously a minus sign is of there, then this into 8, this is plus 0.4 a y cap, and into 15 is minus 0.76 az cap. Okay, minus 0.76 a z cap. So this is basically the vector that I will get, a unit vector of AC. Now I have to find out AB cross cross BC, right? That will actually give me the normal vector AN cap. So what is AN cap? Because I have to divide by the magnitude as well. This, right? This is, I have to divide by the magnitude as well. That I will do after computing the AB cross BC. So what is AB and what is BC? So first I will compute AB. AB is vector B, or I can write OB minus OA, right? So what is OB? OB is 16, and I will just do this directly now. 16 minus of minus 4 AX cap plus 20 minus of 2 AY cap plus minus 5 AZ cap. Okay, minus 5 AZ. So we will get this to be AB is 20 AX plus 18 AY minus 10 AZ. And what about the AC? Not AC, sorry, BC. BC again will be OC minus OB. So this will be equals to can do this now. 6 OC, right? OC is this, right? Minus 14 minus 16 AX plus 10 minus 20 AY plus 20 minus is it. Okay, so BC is equals to minus 30 AX plus minus 10 AY plus 15 AZ. Okay, not 15, sorry, 25, right? 25. now we'll do the cross product. How do we do the cross product? Cross product will be something like this. So I'll do the computations, calculations, then again I will come back. So yeah, finally I have solved the vectors. So first of all, I have computed this in front of you. Then I computed AB vector, VC vector. Then I computed the AB cross VC BC vector. That is a normal vector to both plane AB cross BC. Just hold on a second. I'll just do one quick thing. This before I'm just checking whether it is recording correctly or not, the voice and all those things. So yeah, all these are recording correctly. So then I computed this AB cross BC vector. Then again I computed the unit vector of this particular thing, and then I did the unit vector cross product of both AAC and AN cap. Then I got back my vector AV cap. That is my answer. This is my answer, right? This is the vector that is both perpendicular to the vector AC and in the plane of triangle ABC. So this is actually a good teaser question, brain teaser question. So this type of question will not come in the examination because this is very lengthy, but obviously this is good to have a good practice on. Okay, so this was it about the questions. Now I will do few locuses of different coordinate system. So if I have a Cartesian coordinate system, in a Cartesian coordinate system in 3D I have three axes: x-axis, y-axis and z-axis. Now if all the 3 points are fixed, then what I get a point basically. So I will move in the x direction alpha, I will move in the y direction beta, and I will move in the z direction gamma, and I will get back a point. This is the location of the point. Okay, I will get a point if all the 3 points are fixed. Now if one of the variable x, y and z are basically variable locations are varying, then I will get a 2D thing. This is a 1D, one dimensional thing. Point is a one dimensional object. If one thing is varying, right, and two things are constant, I will get a two-dimensional object. Okay, what is this? If x is varying, from how much x can vary? We are talking about real numbers here. So x can vary from minus infinity to plus infinity. So minus infinity to plus infinity, I get back a whole line. Okay, y and z are fixed. Obviously, I will move y by beta and z by gamma. But my x, right, can go from minus infinity to plus infinity. It is totally like a line. What do I call this? This I can call also a line parallel to this is a zero dimensional point. Is a zero dimensional thing, right? Sorry, and line is a one dimensional thing. Why line is a one dimension? It has only one dimension, right? Like I can define the line by a length. It has only a length. Okay, it has no two things, only one thing. So yeah, sorry for the mistake. So what do I call this? I can also call this a line that is parallel to x-axis. Line that is parallel to x-axis. Okay, this is what I call basically this 1D structure, right? You can do it for the other axes as well. If you vary y, then you will get a line parallel to y-axis. If you vary z, you will get a line parallel to z-axis. Okay, just hold on a second. Yeah, everything is fine. Now let's come back to the equation of line in 3D. So this thing, right, this thing you should know. It's good to know, actually good to remember. So you should know this thing. How can I write the equation of a line in 3D? Because I know how to write the equation of a line in 2D, okay, in x and y. Because how do you write the equation of a line? You write y equals to mx plus c, right? If you remember, to write equation of a line in 2D, you write y equals to mx plus c, and you know what is m is y2 minus y1 by x2 minus x1, or if you know other forms, right, which I have taught in the basics of calculus. If you remember, there I have taught, so those also you can recall. Okay, but this is the most basic form. Okay, so but in 3D you can remember this. This is the easiest way you can remember x minus x1 by x2 minus x1, because obviously you need to have 2 points, right? x1 y1 z1 and x2 y2 z2, right? 2 points I have been given, and between those 2 points I will draw a line basically. Okay, so I'll join the 2 points. So this will be x minus x1 by x2 minus x1 equals to y minus y1 by y2 minus y1 equals to z minus z1 by z2 minus z1 equals to t. Okay, this is how I draw the equation of a line. Rather simple, right? This you have to remember, this you have to recall. So this is an important formula. This can be used sometimes during numericals of our EMFT chapter. So nothing much to mention over here, right? So let's solve one question in other coordinates, right? So because I've given you the basics of cylindrical coordinates, like we have already learned the basics of cylindrical coordinates and spherical coordinates. So we'll do few sums on that. Two vector fields a rho, a phi, a z. So this, right, this actually is in the cylindrical coordinates, rho, phi and z, and n vector is this. Then the value of alpha, beta, gamma for which the vectors are parallel to each other. How does a vector becomes parallel to each other? It should be in the same direction as the original vector. Its magnitude can change, but the direction should be same. Okay, so basically the components should be basically scaled. That's it, right? Magnitude can be scaled, but they should follow the same relations. So here, if I go by the options, the first a rho cap component is -2, and if this is -2, right, if alpha is -2, then obviously I have multiplied a -1 with this m vector to get back this vector, because they are parallel. They will be like, how will be my n vector related with my m vector? They will be proportional by a proportional constant k. This is how I understand that this is a parallel vector. They have to follow this relationship. So k can be a real number, anything between -infinity to +infinity. It doesn't have to be an integer. It can be any real number. Now, if from this option, this is telling me that the a rho cap component will be -2. The second component, right, should, according to this, should be -3, which is again correct. The third component should be equals to -1, which is again correct. So option A, you're observing it correct. Okay. Now, what about option B? So you have to go here, even though this is a MCQ, so obviously option A is correct, and you will proceed in the next question. But let's see the next options. 4, 3, 2. So first is telling 4. So I have scaled this by 2. So the second component should also be scaled by 2. No, this has not been scaled by 2. This is still 3. So obviously this is wrong. Okay. This is wrong. This can't be possible. Again, let's see this component. -2, 3, -1. So again, I'm scaling it by -1. This should also be scaled by -1, but this hasn't been scaled by -1. So this is wrong again. Again, this 0, 0, 0. So this is an interesting fact, that one thing I have to mention here, that k cannot be equal to 0, because if zero vector is parallel to everything, it doesn't make any sense. It doesn't make any sense, because if I multiply this with 0, this will be a null vector, and that will be true. But that doesn't give us any information. That is not a good vector to get a parallel, right? Zero vector doesn't have any definite direction. So I know null vector doesn't have any direction. Why? Because if you try to find out the unit vector, right, you are dividing by 0, and if you divide by 0, everything breaks. All the laws, all the things breaks. So null vector doesn't. So this is the reason why I took this question. Basically, doesn't have any direction. Okay. So null vector doesn't have any direction. So if null vector doesn't have any direction, so k cannot be equal to 0. So I have to exclude the k basically. So what I can do is, I can write it like this. If in this fancy mathematical format, this will be from -infinity. This will not include 0. This will actually exclude 0 and 0, +infinity. If you are not able to understand what is this, what is the meaning, you have to go and watch the basics of calculus. That is obviously present on the YouTube also, free. So you can go and watch that. Okay, basics of calculus. How do we define all these things? So k cannot be equal to 0. Okay, that is an important point. So D is not true. Let's now go to more locuses. So let's go to this plane/surface. So if I have a plane/surface, this is a 2D figure. How 2D? Because two things are varying now. That's why 2D. So x and y both are varying. Let's make z fixed. So if x, I'm going along x as well, I'm going along y as well. So what will this cover? This will be a plane basically. This will be a surface. Okay. So, and what will be this? This will be a plane that is parallel to xy plane, or plane with axis z axis, because I call the perpendicular to the plane, normal to the plane, as the axis. So I can say this is a plane parallel to xy plane, because xy plane is here itself. Okay, and it is parallel. Z can be anything. Okay, so axis is basically the fixed variable, that is the axis. Z axis, Z is the axis of this particular surface. Okay, and you can do the same. You can keep the y constant. You can vary x and y surface will be something like this, right? X and y surface will be something like this. So you can do all this locus. Okay, just to give you overview, how do we draw the locus? How does the locus looks, right? If I keep a particular variable fixed, that I try to explain here. Okay, so few points I have wrote about this locus of plane slash surface is that two coordinates for finding out locus, right, of a plane slash surface, two coordinates must be variable, and fixed variable is the direction normal to the surface. So the fixed variable will be the direction normal to the surface. So here z is fixed, so z axis, right, is the direction normal to the surface. If let's say y was fixed and x and z were variable, then obviously y would have been the direction normal to the surface. Or if you find out minus y, right, that will be also perpendicular or normal to the surface. Okay, so they are anti-parallel. Now this is one important thing that you should know is that let's have r as any vector that is on the surface. R be any vector, position vector of any point lying on the surface, and n cap is the normal vector of this particular surface. N cap is the normal vector of this particular surface. Now if I take the dot product of these two, what will I get? Actually, I want to know what is the distance from the origin to this surface. What is the distance from the origin to this surface? So I need to find out this length, right? I need to find out this length. Okay, so if I find out this length, what does it means? So this means this is basically the length that I want to find. So if I just find out this, let's say this angle, right, this angle with this thing is theta. This angle with this thing is theta, and what is this? This vector is basically parallel to this vector. So if I just bring this vector here and connect them tail to tail, and I just need to find out this r cos theta. Okay, r cos theta, and I will get my desired length. So exactly that is what I am doing. What does r dot n cap mean? R dot n cap means magnitude of r into angle between n cap and r vector. What is that? That is theta, and cos of angle of r vector and n cap. So r cos theta and n cap magnitude is 1 because it is a unit vector. So I will get my magnitude r cos theta, and that is exactly what I want. So this is equals to magnitude of r cos theta. So sometimes this format you will not be able to find out. You have to find out like this. Okay, just simply do the dot product and you will find the distance. So these tricks we should know because this we will use in the main chapters of electrostatics and magnetostatics. Okay, so this was one thing. Another term is surface slash area vector. Okay, what does area vector mean? Although I have given you an overview in the double integration portion of my mathematics lectures, here again I will explain. In surface integrals, when a vector is integrated over a surface, the surface is treated as a vector known as area vector. Okay, so surface is actually a vector, it is not a scalar. Magnitude of the area vector is the size of the surface, basically the area of the surface. Okay, area of the surface. Direction of the area vector is perpendicular or normal to the surface. Simple, right? The normal, I will follow the right hand rule. I will just curl my fingers and it is pointing towards me. So I will curl my fingers and it is pointing towards me. So this normal direction to the surface is basically the area vector. Okay, direction of the area vector. Magnitude I know, direction I don't know, I have told you. So area vector can be defined like this: magnitude, that is the area, and the perpendicular to the area vector, as cap. Okay, so magnitude of s equals to magnitude of surface vector, as cap is equals to direction of surface vector. Okay, so that is this thing, right? I hope you understand. Now equation of surface: if x is constant and y and z are variable, then what will be the, now this, right, I won't be able to comment on the magnitude of the area vector, but I will be able to comment on the direction. What can be the direction? I told you, right? I told you in this short point, the fixed variable is the direction normal to the surface. So I just need to find out the direction normal to the surface, that is basically the fixed variable. So my x axis here, right, my x is constant, so x axis will be the normal to the surface. So ax cap will be the normal, or ax cap will be the normal, will be the direction of the area vector formed by this yz plane. Now this will be plus minus ax because obviously it can be like I can say here itself, because if this is zy plane, right, so it can be here, this side or this side, both are perpendicular, so that's why plus and minus ax. Same I will follow for y, same I will follow for z, same thing will follow. Okay, so I hope you understand the concept of area vector for a open surface. This was for a open surface. This is open surface. I have explained in my vector calculus chapter what does open surface means what does closed surface means. Okay, so that is the thing. Now let's do this closed surface. What does closed surface means? A closed surface is one that completely encloses a volume, separating the inside from the outside. So this side, if you observe this, if you zoom in, this is an open surface, because I am not able to, like, can I hold water in this? Can I hold any water? Can I hold any air in this? No. Can I hold a water in this? If I just somehow I get the water inside this, will this be able to hold the water? Yes. Water will not come outside, it will be inside only. So this encloses a volume. This can hold something, okay, mass or something. So this is a closed surface, as it can enclose a volume. This is open surface, this is open surface, this is open surface. Okay. So I hope you got the difference between open surface and closed surface. For closed surface, we can define the interior and exterior region. So as for this, right, inside will be the water present and outside, let's say, air is present, right? So exterior region is this and interior region is this. Okay. So but how can I define the direction of the surface? Because for open surface it was pretty easy, either plus minus x, right? Plus minus x. But how can I define the direction of closed surface? For closed surface, right, there will be only one direction. It will not be plus minus. Okay. We'll see. For closed surface, we can define the interior and exterior regions, meaning there is a clear distinction between the space inside and outside, space outside it. Okay. So the space outside it, pointing outside the surface, will be the direction of the surface at this particular small surface. Okay. Because this is a combination of many surfaces, so we will talk about small surfaces. So at this particular region, right, the direction of this surface vector will be here. At this particular region, the direction of the surface vector will be here, and so on. But in case of open surface, I am not able to identify which portion is inside and outside, so obviously there will be two directions, but here there will be one. An open surface does not enclose any volume. Examples of open surface include a flat plane, an open cylinder without ends, or any surface that doesn't fully enclose area. So a closed cylinder can enclose area, and I can easily define the direction. So let's do this. Okay, let me draw a cylinder. Now this is a cylinder that is closed, right? This is closed, this is closed. So if I put in some water here, this will totally hold this water. Can you tell me the direction of this top surface? What will the direction? Direction will be outside, pointing outward. So it will be on the top. Okay. I don't know exactly how it is defined in XYZ Cartesian coordinate, but something like this. Okay. The direction of this bottom portion, it will not be like this. It will be pointing outward, right? Perpendicular but pointing outward. Again, the direction of this particular curved surface, this will be pointing outward. Okay, this will be pointing outward, pointing outward. Okay, like this, direction will be present. Okay, now here, if this was open, then I wouldn't have certainly said what is the direction. I couldn't have commented what is the direction. So let's say if this top and bottom is not there, just this curved nature is there, right? Top and bottom lid are not closed, they are open actually. So the direction can be this, direction can be this. Here there is no surface, this is open, okay, air can go inside, this is open. Okay, so this has direction here and here as well, direction here and here as well. Okay, so not any defined direction now, because it cannot enclose any volume, it cannot store any water. Okay, so open surfaces can have electric flux passing through them, but unlike closed surfaces, they don't contain any well-defined interior region. They don't have any interior region. About this electric flux, though, that I will talk later. Just electric flux, you can talk about water. Water can go inside and then go outside of the open surface, right? I cannot store the water, but in closed surface, I can store the water. It will be similar to flux. Okay, so this was a short concept. So in this lecture, mainly I am talking you the miscellaneous concepts that has not been covered or that has not been given enough time. Okay, so those I have covered. So previously we are obviously covering the base lecture by lecture. So another important concept is differential length. So if I want to define a small length in the x direction, I define it as dx, I define it as dy in the y direction, and in the z direction as dz. Now if I want to write in the vector format, how do I write it? So dl vector, right, will be something like this. It will be dx ax cap plus dy ay cap plus dz az cap. Okay, so this will be the dl vector. Okay, small differential length vector. This is the vector format. Okay, vector format. X direction I have defined, y direction I have defined. Now if you for some cases, let's say it is not changing in z direction. So if you want only in xy direction, you will write it dx ax cap plus dy ay cap. And similarly, if it is only changing in xz direction, you will write dx ax cap plus dz is az cap, and so on. Okay, now let's come to very small area, differential area. Now we talked about differential length. Now we'll talk about differential area, which I just mentioned, right? Surface vector. But that was for a big surface. Now we are talking about small surface. So for a very small surface, how do I define a differential area? It will be dx dy in the xy plane, parallel to the xy plane, and what will be its direction? Again, plus minus az cap, as mentioned, as taught you in the just at the starting of this lecture, and same as in the yz plane, same as xz plane. Okay, you can understand this. But your surface vector can be in some other direction as well. Let's say if it is not in az direction, if it is not in y direction, if it is not in ay direction, then how will it define? I will talk about that. Don't worry, I will talk about that as well. Okay, now let's come to differential volume. So if I have a small box containing volume, so how do I define it? So volume, right, it actually doesn't have any direction. It is a scalar quantity. Why? Because how do I define the direction? Because for this surface the direction will be here. For this surface the direction will be bottom. This here. Volume, like this has so many directions. So how will I define the direction? I cannot define the direction. It will be simply a scalar. Just the magnitude of the scalar will be dx dy dz, because in the x direction small length is dx, in the y direction small length is dy, and in the z direction small length is dz. Okay, so like simply cube is there, you can multiply the sides of the cube and you get the volume of the cube. Okay, so if a surface encloses a volume, then the area vector should always be directed outward. So this I have already established in the previous portion of this lecture. So this already have been established, right? The surface vector should be pointing outward of the volume if it is a closed surface. Okay, so magnitude of surface vector I have already taught you. Now can you pause the video and solve the magnitude of surface vector for the for these three examples? Can you pause the video and solve these three vectors? Okay, so how do I solve this? So this is simply a square. So what will be the magnitude of the surface vector? Magnitude of the surface vector will be simply a times b, ab. Here this is simply a triangle, so magnitude of the surface vector will be simply ab by 2, half ab. Okay, and here this is simply a circle, so magnitude of surface vector will be pi r square. Okay, so these are simple things only, you will be able to do it. Now for any random shape, these were known shapes. If I have any random shape, how will I find the magnitude of the surface vector? These have been already taught in double integration. So here also I will say, for any random shape, you will just take a small differential length, in whichever plane it is lying, you will take the differential surface of that particular plane, and then you will integrate that. So this is, let's say, a region R, and you will totally take a small block. Okay, very small block. Let's say this is currently in the dx dy. You will take a very small dx dy block, and you will simply integrate this. Okay, so what will be this? This will be magnitude. This will be r. Area will be simply dx dy. This I have already taught in the double integration portion, if you remember, right? Dx dy. So I'm not explaining it much, but we know how to find out this thing. I have solved multiple questions like this. Okay, now let's solve the direction. So direction, right? For open surface as well, we can fix the direction if the orientation is given. Okay, so here orientation is not given, and this is lying on the zy plane. So what will be the direction? Here the direction of the non-oriented surface vector will be plus minus a z, not a z, ax cap. But here what will be the direction? Here, right, as the orientation is given, I will follow my right hand. So I will rotate my right hand like this. Okay, not like this, like this. Okay, so this right hand I will rotate like this. So this is going inside, or this is going in this direction, right? In this direction. So this is minus ax cap. So just following the right hand rule, right? Just rolling my fingers, and my thumb is pointing towards the screen, or this is going away from the screen, right? Not towards me, away from the screen, going inside the screen. If it is going inside the screen, obviously this is in the opposite direction of x. So this will be minus ax. okay, minus ax square. So this is how, if the orientation of the surface is given, I can surely say that what is the direction of the particular surface. Okay, so now we'll learn about different coordinate systems. So I'll give you a brief overview. So 3 coordinate systems we have. I know you have already learned, I think, from Himanshu, but still I will give you a bit of overview. One is Cartesian, another one is cylindrical, another one is spherical. So in Cartesian, xyz is there, we move in the linear fashion, right? Linearly in the x direction, linearly in the y, linearly in the z direction. But in cylindrical, what happens? We move in the cylindrical way. Okay, that's why the name cylindrical. So rho means the radius of the cylinder. Phi means the angle that I move from the positive x-axis, that I needed to move from the positive x-axis. This is the rho and this is the phi. Okay, and z is z, same as the previous case, just moving linearly in the z-axis. So I have just converted my x, y, z in rho, phi and z, and I can define any point on the 3-dimensional space with the help of rho, phi, z, same as x, y, z. Okay, but this has some advantages of symmetry, so obviously we need to learn this. Okay, and spherical as well. Spherical is just a sphere. Okay, the difference is here there are 2 angles. Now this phi, right, this phi was actually not in linear fashion. This was not in linear fashion. Again, this r is again the radius of the sphere. Okay, yeah, sorry for the interruption. Actually this, right, this should have been theta and this should have been this should have been phi and this should have been theta. There was a mistake, printing mistake. So what is theta? Theta is the angle from the positive z axis. Okay, and this range will be from 0 to pi only. This here phi range will be 0 to 2 pi, because I can totally cover this whole cylinder, and z will be from minus infinity to plus infinity. Rho will be from 0 to infinity, because if I move from, if I like, you may ask why phi is not negative, because if phi is negative, right, that means I have not previously covered this particular point, but actually I have not phi, sorry, rho. If rho is negative, that means you are telling me that I have not previously covered this point, but actually I have. How? This phi will rotate and come back here, right? This rho is, let's say, 3. This 3 will be here as well if I rotate by this angle. So actually I am covering with the help of phi. So I don't need rho to go negative. Phi is enough for me. So that's why the range of phi is, so range of rho is 0 to infinity and phi range is 0 to 2 pi. 361 complete circle. And this theta range is 0 to pi. Why? This theta range is 0 to pi because this covers this whole thing. Okay, now this phi is already covering this other portion, right? That's why theta doesn't need to go whole 360. This phi is already covering this whole 360, right? So I hope you get the point, and this I have explained in the previous mathematics basics as well. That's why I'm not going too much in depth here. Okay, so ranges will be this, and our range again same as rho will be from 0 to infinity. Okay, so now let's do the locuses of cylindrical coordinate system. So in cylindrical coordinate system, again, if one thing is varying, it will give me a one-dimensional figure. Let's say if z is varying. If z is varying from minus infinity to plus infinity, and rho and phi are constant, so my distance from the origin, rho is the distance from the origin, and phi the angle that I move from the positive x-axis, these two are fixed here, and my z is varying, I will get a simple one-dimensional line. Okay, I will get a line. I will get a line. Okay, so next, if this, okay, if this phi and z are constant, let's say the angle that I move and the z, right, from the z axis, the distance from origin to z axis is constant, then if I just keep on varying my rho, I will again get a line. I will again get a line. I will get a 1D structure. I will get a 1D structure. I will get a line. Okay, this is 1D. This is 1D line and 1D. But what if my rho and z are constant, that is the distance from the origin and the height from the origin, both of them are constant, but my phi is varying, right? I'm just rotating from 0 to 2 pi. Obviously I will get a circle. This is like a ring, actually not a circle, this is a ring, right? I will get a ring, actually a ring. This is still a one-dimensional figure, still a one-dimensional figure. So I hope you got the point. If one thing is varying, I will get a one-dimensional figure. Now if two things are varying, if z is constant again, and if rho and phi both are varying, so if rho is also varying and I am also rotating, so I will get multiple concentric circles that will give me a disk. This will be a 2D figure, disk, and 2D. So these things you should know. You should be able to identify what I am actually getting by varying. So this you have to visually understand, right? Mentally, like in your brain, you have to understand this visually, that what is happening if this is varying, right? Because this will help in the actual electrostat and magnetostat part. Then if my rho is constant and phi and z are varying, so z is varying and rho is constant, so I'm moving in this direction, right? And rho is constant means the radius of the circle is constant, but I'm moving in this direction. I will basically get a hollow cylinder, which is again a 1D structure. Next, if my phi is constant and rho is from 0 to infinity and z is from minus infinity to plus infinity, so phi is constant, the angle that I need to rotate, that I need to rotate is constant, but rho is varying from 0 to infinity and z is also varying, right? So basically I will get a plane. This will be again a surface. I will get a plane, and this will be again 2D, right? Again, if my if my rho is varying from 0 to infinity, rho should be constant, here rho should be constant, yeah. If my phi and z are varying, is this okay? Okay, no, here, right? What I meant to do here is everything is varying. If all of them are varying, what does that means? If rho is also varying, okay, my phi is also varying, my z is also varying. If all of them are varying, that means basically I will get a solid cylinder, and like this will also the radius will also keep on increasing, right? So I will basically get a 3D structure. I will get a solid cylinder and multiple solid cylinders, right? So I will get multiple okay. So this is a 3D structure. This is a 2D structure. So this is not 1D, this is 2D, right? 2D, okay, and 3D. Obviously, three things are varying. I will get a 3D structure. And can you identify? I will pause the video. Can you identify what shape I will get here? What shape I will get here? If I vary the following components, right? Just pause the video and try to solve by yourself. This is in the spherical coordinate system. Okay, I hope you have solved by yourself. So this one, right? This one will be actually a ring, because here r and theta are constant. Basically, the radius and the angle from the x-axis is constant. So angle will be, this point will be defined here. This point is constant, right? But this phi is moving. So again, I will draw a line here. This angle will be theta, but this point is of some different phi, and this will keep on happening, and I will get a simple ring, 1D structure. Again, if r and phi are constant, so the distance from the origin and the angle from the positive x-axis is constant, I will get a semicircle. Why? Because theta variation is only from 0 to pi. So theta can vary from 0 to pi. So I will start from here, and then again I will go here, right? This particular thing is called as a semicircle or a semi-ring. This is again a 1D structure. Again, if my theta and phi both are constant, but my r is varying, the distance from the origin is varying, but this angle from the positive x-axis and the angle from the positive z-axis are constant. So this will be basically a line. Okay, next up, if I talk about locus of 2D structures. So if my phi and theta both are varying, if my r is constant, so if theta is varying, that means my angle from the positive x-axis is varying like a semicircle. Okay, and then phi is also varying. This semicircle will actually cover this whole particular region. So this will be basically what? This will be basically a hollow sphere. This is a 2D structure. This is a surface. Again, if my r is varying, going from 0 to infinity, and my theta is constant, my phi is varying. So if phi varies, I will totally, like, if r is constant, the distance from the origin is here, not constant, sorry, distance is varying, right? Distance from origin is here, but the theta is constant, right? Theta is constant, so I will be on at this point only, but I will rotate a full 180 due to this phi. Again, not 180, full 360. Again, r will change, my phi will rotate, but theta is constant. Again, r will change, my phi will rotate, my theta is constant. So I will basically get a hollow cone. This things, right? Few things you have to visualize by yourself as well. Again, if my what is this? If my phi is constant, r and theta both are variable. If r is variable, again the distance will, like, it will keep on increasing. I will get multiple what? Semi rings. I will get multiple semi rings. If I get multiple semi rings, basically it will be a semi disk. That's it. Okay. Again here, if all of them are varying, as the coordinate suggests, I will get a sphere. Okay, this will be a solid sphere. This will be a 3D structure. All these things will be 2D structure as two things are varying. Just simple relationship. I hope you understood. These things you should have a grip idea of. Now let's do the unit vector conversions. So what are the unit vectors in different coordinate systems? So in cylindrical, the rules are same. Okay, as Cartesian coordinates. So if I just take the dot product of two unit vectors along arrow cap. So what is arrow cap? Arrow cap is in this direction. Arrow cap is in this direction. The direction perpendicular to the surface, right? Perpendicular to the surface of this cylinder. That is the direction of arrow cap. What is a phi cap? What is a phi cap? A phi cap will be in this direction. The direction in this direction, right? In this angle direction, right? In this direction. The direction of this phi. What is AZ? Just the direction of the Z axis. Simple, right? So all of them will follow the simple rules that the XYZ follows. The dot product will give them the dot product of the unit vectors, basis unit vectors will be equals to 1. The cross product will be simply equals to the dot product of similar basis vectors will be 1. Okay, because they don't have any angles, but the dot product of the dissimilar, that is rho phi, will be basically 0. Why? Because the angle, you will observe that they are always perpendicular. Z, rho and phi are always mutually perpendicular. So obviously cos 90 is 0. So that's why the dot product of the non-similar vectors will be simply 0. Next, arrow, a phi and az. So if I take the cross product, if I do the, like, this will again follow the simple that right hand rule, right? If arrow cross a phi will give me az cap, az cross arrow will give me a phi, and so on. If I just flip this, if I do this, arrow cross a phi, so I am going in the reverse direction, so obviously I will get az cap but negative az cap. Okay, how you can do? You can identify here as well. So if I do ar cross is a phi, so ar cross a phi, so I will rotate my hand like this. Okay, and I'm getting positive z direction. R is in this direction and phi is along the cylinder, so like this I'm getting top. So top is this, right? Top is this, so az cap. But if I do a phi cross ar, so a phi is like this, right? A phi is this correct? No, a phi is like this, right? I have to rotate my hand like this, so I am going in this direction and I am coming in the r direction, right? So it is in the downward. So if you do this, your hand will break, but I have tried to visualize, right? So I am coming from here, a phi cross ar will give me in the minus az, and exactly that is what I mentioned here as well. Okay, so that thing I wanted to follow. So if I go in this anti-clockwise direction, I will get minus, and if I go in the clockwise direction, cross product. This is for the cross product. The top one was for the dot product. Okay, cross product. Okay, and if I want to define a vector in the cylindrical coordinate system, I can define it like this. This has been already explained, so I will go a bit fast here. Okay, and same for spherical as well. All these things will same follow. Just here, I will have ar cap, a theta cap, and a phi cap. These three vectors will be there. Everything else will be same, and all three unit vectors will be orthonormal to each other. Okay, now let's like I have already mentioned, dot product of unit vectors. Okay, basis unit vectors. Dot products of basis. They are known as basis because they are covered the. With the help of basis vector, I can define any vector. That's why they are called basis vector. So cylindrical coordinate, dot product of two vectors will be simple. M dot n will be m rho into n rho, and m phi into n phi, and mz into nz. Same simple, right? Dot product is not as simple. Spherical dot product will be also simple. Okay, but in cross product, things become a bit not only difficult. Things are still simpler here, but things will be different when we will take the gradient and all those things. Okay, cross product also just like xyz, we write a rho, a phi, az. Here ar, a theta, a phi, and the same procedure which we should do xyz, I have just replaced with rho, phi and z. Here r, theta and phi. Nothing else. Okay, so I hope you will be able to do this. Just a new thing, new coordinate. That's it. And how do I define the differential length? Now the differential length will actually change. How it will change? So here my dl vector, right, will be d rho cap a rho, because this is just in the direction. This is a linear thing, right? As this is linear, so the differential length of rho will be d rho. Okay, but this phi, right, is not linear. This is a curvature type thing, right? So can you tell me the length of this? If you remember, can you tell me the length of a arc? Okay, if the radius is r of this length and the angle by which angle of the arc is theta, what is the length of this arc? What is the length of this arc? If you remember, it was r theta. It was r theta, right? And exactly that is what I will do, because I know the differential length in the phi direction, that is d phi. Okay, d phi, I know the differential length in the phi direction. Like I will just increase this angle by d phi. I will increase this angle by d phi. Okay, I will come somewhere around here. Come somewhere around here. Just will reduce the somewhere around here. Okay, this will be d phi. If I am able to write this, right, d phi. But what is the length that actually increased? What is the length actually increased? This length, right? This is the length that I am interested in. I'm not interested in d phi. So the length actually is now this radius times the angle change. So radius is how much? Rho. Radius is rho. So rho times d phi will be the changing length, and z direction component is same only. Okay. Now how do you write the differential area? What do you do? Okay. Just to simplify things, you can obviously visualize it, all those things you can do, right? You can visualize the area, all those things, but that is the homework for you, how to visualize the surface rho equals to constant, how to visualize the surface rho phi equals to constant, z equals to constant, that I have shown you previously. Just try to visualize a small area here, right? When my rho was constant, sorry, where? Here, not this rho, where was rho constant? Rho was constant here. So can you visualize a small surface here, small surface? Okay, that is what I will show you here. I will just directly write it. Okay, just to simplify things, I will directly write it. If you want to find out rho equals to constant, if you know, remember the simple point, right? What point I wrote you? The direction of the surface will be the direction of the axis, which is constant. So here rho is constant, so direction will be either plus minus arrow, and as soon as you get back arrow, right, you just cover this thing up and write the other two components. Write the other two components, that will give you the differential area. That's it. Okay, what do you do? You cover this one up, okay, and then you write here what? Rho d phi, and you write dz. That gives you the magnitude of the differential area. Direction will be the constant. Okay, that's why I told you the point. You can visualize. I recommend you to visualize, but this is the simplest way to remember. No need to remember, I have visualized as well, but just for exam purpose, you have to follow this. That is the better way to follow this. Okay, again, if phi is constant, if phi is constant, right, what will be the direction? Plus minus a phi, plus minus a phi. Again, you cover this a phi direction and you take the other two components, d rho and dz, and same for the z component as well. And differential volume is just, you simply multiply all these three components and you will get the differential volume. This is d rho, d phi, and dz. Rho d rho, just have to write this in proper structure, right? That's why I wrote it rho d rho, d phi, and dz. Okay, that's the differential volume. Okay, so that's how we do this. And for spherical, right, again you follow the same rule. Again here, one interesting fact over here is this thing is actually a bit wrong. This should be actually phi. This should be theta. And this should be phi. Okay, so here what is the important point over here is I know the differential length of d phi, that will be rho d phi basically. This much I know in the a rho cap direction, right? I know r will be same as rho only, but it is on other direction as well. So it will be simply dr. This is a linear length, right? If I increase it incrementally, it will linearly increase. So this is again dr. But what about this theta? Again, if you observe, if I increase this incrementally, okay, here, if I increase this incrementally, this is d theta. How much will this increase actually? Again, what is the radius? Radius is r. So how much will this increase? This will increase by r d theta, and exactly that is what is written over here. Now remember, this is actually rho d phi, right? This rho and r are different things. This is rho, this thing is rho, okay, and r is actually different, right? So if rho and r are different, what is rho? Now this theta is actually angle with respect to the positive z axis. So r cos theta is this z component, and r sin theta will be this component that is lying on the plane. So rho actually is equals to r sin theta. This have been already explained, I hope, in the previous lectures. So I'm not going too much in depth here, right? So r sin theta. So I'll just replace this row with r sin theta. So I'm just telling you how to remember, okay? Not exactly mug up the thing, how to remember this conceptually, okay? So this will be r theta, this will be r sin theta, and d5 will obviously be present. And again, you follow the same procedure just mentioned in the previous slides, and you will get back your differential area, you will get back your differential volume. Okay, same procedure. Now we'll give you a few things as homework. Do this, take the screenshot and do this as homework. And in the next lecture, I will solve this question. I will like this, right? This thing also we'll learn in the next lecture because the time has been gone. So we'll learn about this position vector, and if you know a bit about position vector, I will give you this question also as homework in the next lecture, and you will solve it in the next lecture. Okay, so that's it about this lecture, and I will see you in the next lecture. Thank you for watching and happy learning.